Official members bounce, bust off the chrome. Realize it's real hell where we call home.
Official members bounce, bust off the chrome. Realize it's real hell where we call home.
From the heart inside one, I vision fat licks and mat clips. The chroma make the average imitator do backflips. You lack a pistol, so put a vest around the issue. Slugs will never miss you. Coming from members that's official.
Okay, so today we're going to talk about SQL. This will be the only time in the semester we really discuss, like, at the application level. But again, I'd feel like I'd be doing you a disservice if you graduate from Carnegie Mellon taking a database class and never touch SQL. So we're going to cover SQL today. But again, as I said last class, I'm assuming everyone already knows the basics of SQL. And so we're going to focus on the more modern things you can do with it. And that'll be related to homework 1 that's going to go out today. So last class, we talked about the relational model. I went on how great it is and why it's the superior choice for any database system. And then we showed how relational algebra was the building blocks we would use to run queries and to manipulate the database. And then later on in the semester, we'll see how we design a system, basically the query engine, the execution engine, to execute those relational operators in relational algebra and produce results for applications. Okay? So today's class, we're not really going to touch on relational algebra, but you'll see how the things we talked about last class, like a projection and select operators, where clauses, you'll see how they could be the underpinning for relational algebra. We'll go in more details how to implement the execution engine later in the semester. Okay? All right. So some quick background history of SQL goes back into the 1970s. As I mentioned in the last class, when Ted Codd wrote that seminal paper on the relational model, it was all mathematical. He didn't define a programming language. And so other people at IBM took that paper, said, hey, this might be a good idea. Let's see if we can implement a system that could run the relational model and run queries on top of it. But then they had to design their own query language. And as I mentioned last class, the first version of a relational query language that IBM invented was this thing called Square. And this came out of this work done in the UK before System R, which is a very influential early database system at IBM, relational database system. There was another project in the UK called the Peter Lee Relational Test Vehicle, which sounds like it's a prog rock band, but it was an early implementation of a relational system. So they implemented this thing called Square, but as I said last class, you couldn't actually write it. You can't even write it today, right? It's like this vertical language. You have to write things up and down on top of each other, right? So this is the paper that defines Square, and again, it's like weird notation. So this didn't go anywhere. Nobody actually implemented this. But the guys that invented this, Chamberlain and Boyce, they went back and said, okay, let's make one actually for real now. And that ended up being what we now know as SQL. The first version of SQL was not SQL as we understand it today. The first version was spelled out SEQEL, right? And then when IBM came out with DB2 in the 80s, we'll talk about later, they said, hey, now we support SQL. It was SEQEL. Somebody already had the copyright for that, and they sued them. So then they just shortened it down to SQL, right? So this first version will be more true to the relational model in that it didn't support JSON because that didn't exist then, didn't support arrays. Right? All of those things we'll see in the next slide came in later updates to the spec. So IBM built a system called System R. Again, we'll cover that throughout the semester. That's where they invented two-phase locking, a lot of early stuff that we're going to care about in this class. But then they never commercialized System R because they were making so much money on IMS. Even till today, IBM makes money on IMS because there's all these banks and insurance companies, the Social Security Administration for the federal government. All these systems run on IMS, which they set up in the 70s, and it's too expensive to get off of it, so they just still run it, and IBM milks the maintenance fees. But then in the early 80s, late 70s, they realized, okay, the relational model is going to be going somewhere. So IBM put out a bunch of different systems. System 38 didn't go anywhere. SQL DS is still around. But the big one is going to be DB2 that came out in 1983. And that's still around today. And that's still a juggernaut in industry. Again, we'll see DB2 stuff later in the semester. And as we go along also too through the semester, you'll be able to see what makes what I'll call an enterprise database system, like an Oracle or a DB2 or a SQL server, what makes them better, so to speak, against like a Postgres or MySQL, because they're going to have way more advanced features. Postgres is good, but it doesn't do everything that like DB2 can do. All right, so again, the first paper on SQL came out, I think, in 72, 73. And then in 1986, this was designated as an ANSI standard. right? The American National Standards Institute, and then it became a international standard in 1987. And this is where they decided they had to call it SQL, as in structured query language. And so SQL is not a dead language, right? Even though it's standardized in '86, there's been a bunch of new updates to the spec that have come out every so often. And the last one actually came out last March in 2023, right? And you can kind of see here over the years the various features that they've added. And because this is they're addressing the changes in how people write applications and what features they would want in a query language or databases, right? XML was the hot thing in the late 90s, early 2000s. So they added support for XML. JSON was the hot thing, with MongoDB in 2010, and so forth. So they added JSON support. In 2023, they've added support for property graph queries. So now you can do sort of, if you know Neo4j or Cypher, like you can now traverse a graph built on top of tables all through SQL. They also added support for multi-dimensional arrays. As far as I know, at least as of 2024, the only system that supports property graph queries is Oracle. Right? Oracle got their version of what they wanted, and they worked with the standards body, but they're the only system today that still supports, or right now that supports property graph queries. So if you're building a new system today and you say you want to support SQL, the bare minimum you would need to support is what we'll call SQL 92. That has all your favorite things, the selects, the froms, the group bys, aggregations. Right? That's the bare minimum you need to say, my database system supports SQL. It's pretty simplistic. And so, as I said before, SQL is not a dead language, although every year or every 10 years or so, people keep proclaiming it's going to be dead, it's going to get replaced. Google just put out a paper this week, I think, on they have a rewrite of SQL that that they're going to run internally that makes it look more like pandas. Right? There's always somebody saying they're going to replace SQL, and it hasn't happened. So you see a lot of like this guy saying that natural query languages are going to replace SQL, right? This guy is saying he saw a demo of someone using ChatGPT to rewrite SQL, right? And that's all going to go away, or SQL is all going to die. I assure you that SQL is not going to die in your lifetime. I've made public statements about this. It's printed. So it was here before you're born. It'll be here when you die. Now, this may not mean that everything you're going to always do is going to be writing in SQL. And in fact, I think using something like ChatGPT to get a first approximation of what a query should be is a good way to get started. But you still have to put the right controls in and understand, is it actually producing the answer you want? So in the same way that, I think in the long term, in the same way that you wouldn't write assembly now, but there's people that still do it, and you need to know it, SQL might be something like that. But in the short term, it's super important. Unless you think I'm also being that I'm not practicing what I preach, I've already started teaching my 4-year-old biological daughter how to write SQL. And so this is her first SQL query. She's only 4. So her first SQL query that she wrote earlier this year. Now I realize me showing you like my child is annoying, so I'm not going to do that. But she needed some help, and there you go. That's your first SQL query. What do you think?
That's cool.
That's pretty exciting.
Yeah.
Yep. Good job. Your father loves you. Okay. So, all right. So in the SQL spec, what do you get? It's not just the select statements and insert, update, deletes. You get sort of roughly categorized as three groups of types of queries. There's the data manipulation language. So these are going to be the selects, the updates, the inserts, deletes, all those. The data definition language, the DDLs, this would be like the create tables, create indexes, create views, the things that allow you to create constructs or create entities within your database. And then there's something we're not going to focus on too much, but the data control language. This is like ACLs for SQL. So some systems allow you to specify who's allowed to even read what table, read a column, or even read an individual record in a row. You almost think they're like where clauses, like can this person read anything from this date or something? And then it'll prevent you from reading stuff. One thing we talked a little bit last class, but we'll see more of this today, is that although the relational model is based on sets, meaning that there wasn't going to be duplicates, because it's all math and it's easy to compute that, SQL is going to be based on bags. A bag is an unordered set where there could be duplicates. Right? Lists can have duplicates, but they have defined an order. Sets cannot have duplicates, but they don't define an order. And the bags can have duplicates, and they have no order. And so we'll see some cases where we could run the same query multiple times on the same database, just maybe at different times of the day when the system has reorganized things, and we'll get back different results. And from SQL's perspective, the data system's perspective, it's still the correct answer. Right? If we cared about the order of something, we're going to have to add order by clauses or other things to enforce the, remove duplicates and enforce the order that we're going to want. So we'll see that in some cases as we go along. All right, so today's class, again, this is just going to be a sort of crash course on what I call modern SQL. This is like the SQL++, the things you really need to do to get SQL to do manipulate the data and use data in the way to answer really complex questions. So let's first talk about aggregations with group bys. We'll talk about how to deal with string, date, and time operations. And one of the things we're going to see with this is that although there is a SQL standard and the basics of SQL queries will be the same across different systems, once we get into like dates and times, it all falls apart, right, across all these different systems. We'll look at output control and redirection, window functions, nested queries, lateral joins, and common table expressions. So again, these bottom four here, this is what I would call super important for understanding how modern SQL works. So for today's class, we're going to use a really simple database, modeling a university. There's a table for students, and there's a table of courses, and then students take courses and they get grades, right? And we have really simple data with a small number of rows. And we'll use this as our examples as we go along. All right, so aggregation functions are a way to basically compute a single value that's derived from a bag of tuples or multiple tuples. Right? So this is things you would expect, like averages, min, max, sums, and counts. Right? Sometimes you can do standard deviations, geometric means, and so forth. Like different systems will have different aggregation functions, but these are considered the core 5. Some systems also let you define user-defined aggregates, UDAs. So if there's some computation that you want to perform across tuples that isn't available in the SQL standard or these basic aggregates, you can extend the database system to support those things. That was actually one of the main ideas of Postgres from the 1980s. What made Postgres different from other systems is its extensibility. And we'll see how people have leveraged that over the years as we go along. So here's a really simple example, right? So we want to get the number of students that we have in our table where they have their login ends with @CS. So it's trying to find all the computer science students that are enrolled in classes. So we see we have a count function, the count aggregate here, and we're putting it over a login. This is actually meaningless. Because you think, what does it mean to count a login? You're just counting tuples, right? So you could replace this with a star or a 1. It doesn't matter, right? It's still all the same. And then you see here in the where clause, we have login, and then this like operator is how we do wildcards in SQL. You can do more complicated things like regular expressions, but the basic SQL syntax is say like, and then for whatever reason, the % sign is what a wildcard is. Right? If you want to match, it'll match. I think it's 1 or more characters, including none, and if underscore will match only 1. Right? You can put other crazy things in the count function. You can do 1 + 1 + 1. Right? Again, it doesn't mean anything. The database system will just ignore that computation if they do it correctly. And all of these will produce the same answer. So say now we want to get the number of students and their average GPA that have an @CS login. Right? So you can put multiple aggregates in here. So we can get the average GPA and then count the number of students, right? And we'll get an answer like this, right? All pretty simple. But now we need something more complicated. Say we want to get the average GPA for all of the students that are enrolled in each course, right? So what do? We add the course ID to our select output, projection clause. Is this correct? No, right? What does this mean to say, right? What I'm trying to do is get the average GPA per course, but then I'm having the course ID along with it. But again, the average is being calculated across all the records. The database doesn't know what you mean, like that you're trying to get a course ID out of this, right? So some systems will allow you to do this. Yes?
Going back to the previous slide, is like going to look for substrings, and why do we need a wildcard in the front but not the back?
The question is, what is that like actually doing? Is it looking for substrings? It's looking for any string that'll match a wildcard followed by the suffix @CS. So if I just do like @CS, I think it wants to do a whole match. It'll be an equals operator. The % sign makes it do a wildcard. All right, so going back here, right? So this example here, if I'm trying to get the average GPA of a student in each course, if I just put the course ID here, it doesn't mean anything from SQL's perspective because it's collapsing the average function is collapsing all the tuples down to a single value, and then I'm asking for the course ID from any of those tuples, right? So you could do it. The right way to do this, this is the course ID here is meaningless. If you don't care what the actual value is, SQL now allows you to put this any value in here. But without that, this is technically going to be an error, right? Because again, it doesn't know what course ID you want. And we can just pop open the different database systems and see what happens. So, I'm going to have on machine running back in my office, I have Postgres, MySQL, SQLite, DuckDB, SQL Server, Oracle, and ClickHouse all running. And again, these are all what you would call relational database systems that all support SQL. If we take that query we showed before, and we run it in Postgres, right? Postgres is going to complain because again, I have that course ID in the projection clause, the output, and because it doesn't know how to compute the aggregate on it. It doesn't know which one to give you. But if I add that any value on it, operator, then it'll produce a result, right? But again, what does that mean to have 15445 in there? Like across all the average GPA across all the courses, that's sort of meaningless. So if I can go now to MySQL, right, do the same thing, MySQL gives me an answer right, without the any value. Is that correct? I mean, MySQL seems to think so. But so in MySQL is going to be one of the biggest offenders of like doing weird stuff or incorrect things. And so they have different SQL modes. So if I say I want to follow the ANSI standard, right, then it'll actually throw an error. Or I can tell it I want to be strict to follow the SQL spec. And I can't be spec. It's ANSI. I think that's what you want. Right? It's basically saying follow the SQL spec, and then it'll throw the same kind of errors that Postgres does. We can go to SQLite. We think SQLite's going to do it. He says yes. Gives an answer. Go to DuckDB. DuckDB throws the same error that Postgres does. And DuckDB is actually super helpful. So DuckDB says, hey, if you want to do this, add any value. That's great output. I like that. Let's go to Oracle. Oracle doesn't like that. SQL command not properly ended. That doesn't help. And that's because Oracle doesn't like as, right? What does as do? As is basically an alias. So I'm saying enrolled, but treat it as the name the table with table's names E. But if I get rid of that as, right, then it allows it to work again. Oh, the other student, the other as, right? Then it complains about the aggregation. So let's go now to ClickHouse or SQL Server. SQL Server complains. That's correct. And then the ClickHouse also complains, right? So a pretty basic thing, and they're all producing pretty different results. But it'll get worse. All right, so for this query, what we really want is this group by clause, because what we want is what is the average GPA per course based on the course ID. So we add this group by clause down here. Then we can say group them by the course ID. Now I can reference the course ID in my select output. And then now I'll get the result that I want. Right, so basically what is it doing? It's scanning along our table of all the grades, and it's just going to bucket them up based on this course ID. And then for each of those, it's then going to compute the average and produce the output. Right? So group by, you can actually have multiple columns. Right? You can do multidimensional aggregations. But basically anything that's not going to be anything that's going to be aggregated, produced in the output has to be in the group by clause. Otherwise, you have to add the any value, right? Right. So this won't work because I'm grouping by on course ID, but I'm also now trying to reference name, right? It doesn't like that. So I'd have to put the name down at the bottom, right? You can also now do additional filtering on your aggregations through the having clause. It's like a where clause for group bys. So say I want to get all the students enrolled in the class, and I only care about the classes where the average GPA is greater than 3.9. I can't reference my output up here where it say take the average, alias to average GPA. I can't reference it down here to do additional filtering, right? Because when the data system is actually running this, it doesn't know what average GPA is when it's evaluating tuples, because think of like the aggregation is computed later in the query plan. So it doesn't know how to filter tuples at this point, right? So you can't do this. All you do is just adding a having clause. But this doesn't always work either, because some systems won't let you even reference the aliased output in the projection output in the having clause. Like MySQL will allow this, Postgres will not allow this. What you really need to do, which I don't care for, but you basically have to say, here's the computation I really want, and then do the filtering based on that. And again, in theory, the data system should be smart enough to say, OK, the average GPA you're computing down here is the same as the average GPA up above. I don't need to compute that multiple times, right? In sake of time, we can skip that. But like, again, it's different idioms for these different database systems. And you basically, it'll be, think of this as like without the having clause, they get this output, and then the having clause will do additional filtering. So aggregation's clear? It's a way, again, to compute. It's a way to derive new information from the data that you already have. If people say, I'm a data scientist, or I'm a data analyst, this is more or less what they're doing at a high level, right? You're deriving new facts from the data you've already collected, and allows you to get a better view of what's actually going on for larger trends. All right, so of course, SQL is going to have strings. There'll be basic operations on strings. You can do like equality checks, less than, greater than. There's much other functions you can do to manipulate your strings, or varchars as they're called. All right, so in the SQL standard, as defined in SQL 92, the string cases are sensitive, meaning that the values of the string, we actually care about whether they're lowercase or uppercase. Right? Capital A is not the same as lowercase a. And then the way we're going to reference or to wrap a constant string is through single quotation marks. But you can see from the list here, everybody does something slightly different. Postgres is pretty good at following the standard, so they're going to be case sensitive and only allow for single quotes. MySQL is going to be case insensitive and allow for single and double, and SQLite allows for both as well. All right, so what does that mean? So if, say, I want to check to see whether the name Tupac is equivalent to mixed case Tupac, I can cast both of them to upper, then do my comparison. In the case of MySQL, it doesn't care, right? So let's go back here. Right, so say in my Postgres table, right, select star from student where name equals Tupac. That'll do an exact match, right? But if I change it to be Tupac like that, right, doesn't match. That's expected, right? That sounds good. But we go over to MySQL, it finds it, right? Or do even lowercase, like, or whatever you want, like that, right? Because it ignores cases. And again, this is with their strict mode turned on. I can also use double quotes. Ooh, did that correctly. So if I turn it back to traditional by default, yeah, it'll handle that. But you put it in the strict ANSI mode complaints. So with the double quotes, it's basically saying it's a way to escape the names of columns. Like, I don't recommend this. If your column name has a space in it, you can use double quotes to then reference it. And then let's go over to SQLite. Right, it is case sensitive, but I can still do double quotes. Oop. Oh, that's new. Can't do that anymore either. All right. Hey, every year I upgrade. Fantastic. Good job, Richard. OK. SQLite is a phenomenal system. SQLite is written by one dude down in North Carolina, right? He puts in the public domain. There is a SQLite company, but he put everything in his wife's name. Like all his company is owned by his wife. He's brilliant, and he's super duper nice. OK. So for string operators or do matching, she has questions. Right, for whatever reason in SQL, they're going to use the % sign to match any substring, including empty strings, and then the underscore is going to be matching one character. Yes? His question is, if you're using MySQL, turn on ANSI mode? Yes. Yes. As far as I know, in MySQL is the only one where you can change that SQL mode, just because they're trying to right the wrongs they've done in the past, right? Which is good, right? In enterprise systems like in Oracle, I don't know where you can do this in SQL Server, but you can actually specify what version of the SQL you want from a system. So say you're running on Oracle 22, you can tell it, I'm going to give you Oracle 11 queries. So the idea is you can still upgrade your system, get newer versions of Oracle, but then still not to rewrite your applications as their SQL spec changes, right? And then Postgres just updates every year. All right, so as I said before, there's also going to be a bunch of string functions to do anything you can imagine. Again, think of like string functions in Python to lower, uppercase, lowercase, substring, replacing strings, all those things. All that is available. You can concatenating strings should be like a simple thing, but this is where everyone does something different. The SQL spec says you would use the double bars, like an or. That's how you concatenate strings. In SQL Server, you use the plus, right? Like concatenating strings in Python. And then in MySQL, again, they don't support either of these. You have to use an explicit concat function. Why it's this way? Somebody decided to do it that way long ago, and we have to live with it. All right, strings are pretty straightforward, pretty easy to understand. Other than again when the concatenation stuff comes along. But let's see how the problems we get when you do dates and times. Should be a pretty simple thing to do, right? Seems like kind of important. Databases want to keep track of dates and times of things. You would think the SQL spanner says how to do it, but everybody's going to do something wildly different. So let's try to do something really simple. Let's just try to count the number of days from today, which is August 28th, to the beginning of the year, right? Seems like a pretty simple thing. Let's see what happens. So let's start with Postgres. So the first thing is say, how do we get what today is, right? So the SQL spanner specifies a now function, right? That I can get back a date and time, right? So let's now see if everybody has that. So if I go to MySQL, they have it. Make sure I'm in ANSI mode. Right, they have now. SQLite does not have now. Oracle does not have now. This is SQL Server from Microsoft. Does not have it, or has something. Wait. Oh. All right, we'll come back to that. And then ClickHouse has it. Okay. Well, let's go back to my who didn't have it? Or DuckDB. DuckDB should have it too, I think. Doesn't have it. Okay. So another way to get time is, or the current time is through the keyword, or through this thing called current timestamp. All right. Except in Postgres, it's not a function; it's a keyword. All right. So let's go now to make sure I'm doing the right one. MySQL. They have the function. They have the keyword. SQLite doesn't have the function, has the keyword. DuckDB. Oh, sorry, this is Oracle. DuckDB doesn't have the function, has the keyword. Oracle doesn't have the function, or gives a different error. Date, time, interval, precision, out of range. We'll come back to that one. Let's try it with the keyword. Now we get something else, another error. Yes, sorry.
Which time zone do they follow?
This question, I don't even know time zones. This question is, what time zone are they using?
Because they didn't have the same at some point.
Yeah, so there is a date time type and then a date time with time zone type. So you can say, like in Postgres, you can say, I want to store date time, and I'm explicitly going to tell you what the time zone is. Do that. Always do that. or you can say whatever the default is, like on the system. That's what's happening here. All right, so Oracle is giving me 2 errors, right? It doesn't have select current timestamp with the as the function, and then I got another error where it doesn't like the keyword because it's missing a from clause. So I think this is fixed in Oracle 24. I think I'm running Oracle 21, 22. Oracle does not let you run queries without from clauses. So like going back to Postgres, I can do select +1 like that. And it's like I calculate, I can get any answer I want. And I can do this in all the other systems. In Oracle, you can't run a query without a from clause, without a table. So they give you this thing called the dual, and it's like this built-in magic table that has nothing in it, so that you can write queries against nothing, right? So if I do select star from dual, right, I get some X thing back, right? I don't know what that is. So it's basically it's a way to like to have one tuple to do a query without a from clause. So again, so now I can go select current timestamp from dual, and I get my result. But if I try the function now, right, I get this date time interval precision out of range. Well, what's that? Well, when I ask ChatGPT, it says, oh, you actually can specify the precision of the timestamp that you want, right? So just give me a precision by one decimal place. OK, that's cool. I didn't know you could do that. Let's go back to Postgres and try that, because they don't have the function. Who had the function? MySQL did, right? Right? Can I put 1 there? Let me do it, because they try to copy what Oracle does. But can I do it like this? I can. Right? So I couldn't do the function without the argument. But if I add a 1 there, then I get my result. But everyone's doing something different. So keep going. This one had the function, right? Or no, this didn't like the function. If I add 1, then it doesn't let me do it. That's DuckDB. SQL Server alive. Nope. All right. All right. Don't take this as a knock. SQL Server is a very good system. I don't want to give the wrong impression. So ClickHouse has it. The function does not have the keyword, and it has the function does not have the function with arguments, right? OK, so this just getting the timestamp, getting the current day was a big ordeal across all these different systems. We're still trying to get the number of days since the beginning of the year. So in Postgres, they have a way to get out the day of year. So there's the thing called extract functions. So I can given a date. So here I'm taking the string, today's date. I'm casting it I'm casting the string date of a date into a date, and this extract function says, give me out some part of this date. So I can get out, for example, like the day, and I'll get today's the 28th, so it gets out the date. But I can also get out the day of the year, right? And I get 241, which is not exactly what we want, because it's counting January 1st. We're trying to count from the number of days since January 1st. So what you can do is just cast the beginning, the current date, and the beginning of the year as dates, and just subtract them, and you get 240. That's correct, right? So here's an idiom of Postgres that I do like, where they did even bunch of systems. This cast function, or this, calling this date function, can be a bit cumbersome. They have this nice syntax where you can put a colon after anything, and then it'll cast it for you. Only Postgres can do this, and DuckDB can do it. DuckDB does it because they took Postgres' grammar, right? So then I do that and get the right result. All right, so let's try to do this now in MySQL. I get this. What is that? So for several years, I would do this demo, and I would say, I have no idea what this number is. One year, somebody in the YouTube comments was like, hey, this is what it is. The first number 7 is the current month subtracted by January 1. So 8 minus 1 is 7. And then it's 28 minus 1 is 27. Right? So that's weird. Turns out, so the first way I figured I tried doing this, and you can ask ChatGPT to do it now, but you can convert the dates to Unix timestamps. So that's the number of seconds since the Unix epoch, January 1st, 1970. And then you subtract them, multiply by 60 minutes, by 60 seconds and 60 minutes and 24 hours, and you get 240. There's an easier way to do this. There's a date diff function in SQL Server, or sorry, in MySQL, just to get that. If you try it in Postgres, Postgres doesn't have it. We'll come back to SQLite. This doesn't have a date diff, so what are we in? This is DuckDB. So DuckDB, I should be able to do the same thing I could do in Postgres, right? I can cast it and subtract it. That's cool. If I hop over to Oracle, right? Again, I complains because doesn't have this doesn't know how to cast a string to a date. Well, it turns out you have to specify the format that you want, right? So I have four year digits, five 2 month digits for 2 days. Then I get the answer that way. ChatGPT did that one for me. SQL Server is, let's see if it comes back. Yeah, we might be back. So SQL Server, the way you cast is through this explicit cast function, right? That looks cool. So we get that. They also have a way that you can call convert, but again, Postgres can't. Nobody else can do it. That's a SQL Server thing. So they actually have the date diff function, right? But you get negatives, so we got to do the. I got to put the current year. Sorry, I got to put the first day first, the beginning of the year first, and then subtract it. Do that. So I hope you're getting the impression that, like, as great as SQL is, this is kind of annoying. And then ClickHouse. Right, we get today, which is just, it's an alias for now, subtracted by casting the string through toDate to a date, then we get 240. So again, something should be really simple. Everybody's doing something wildly different. And even the semantics in some cases of these calculations are different in other cases.
Question.
Yes.
So in the MySQL one, the one using Unix timestamp, in which step is it converted to days? I mean, shouldn't it be like seconds or milliseconds when you use Unix timestamp?
His question is this Unix timestamp function, what is that actually converting it to?
Yeah.
I think it's seconds.
Yeah, but
Let's find out. I guess how would we know, right? That looks like seconds, right? And it's an integer, so it's not milliseconds. So there might be a way to get the Unix timestamp in milliseconds. I don't know.
yeah, this feels like a quite unified way to compute.
This shows what? Oh, sorry?
Feels like a way that can unify all the databases to convert to unit timestamp.
He said this. The way I'm doing this in
Like first converting it to Unix timestamp, then converting back to.
that this be the right way to do this across all different systems. Well, let's find out. Right? Because they don't have. What's it missing here?
I mean, it feels like they're.
Maybe it doesn't like round. It's missing. Hold on, let's get rid of the round because that might be fouling us up. Yeah, to his point, like this seems like something that should work everywhere. Right? I'm missing them. Date. Yep. Anyway, but let's look at it. So let's see how we do this in SQLite. So SQLite did not have a doesn't have. I don't think it had the Unix timestamp function, or I couldn't get the work right. So the way I came up with it, and then if you ask ChatGPT, ChatGPT came up with the same thing. You actually want to convert the timestamps into the Julian calendar. If you know what the Julian calendar is, it's the number of days since Julius Caesar's birthday, right? You laugh, but hold up. This is how a lot of the banks in the 60s, 70s, and 80s calculated interest, right? Because I think there's always 30 days in a month in the Julian calendar. It's always a fixed number, whereas the Gregorian calendar, it varies per month. So they would compute interest based on the Julian calendar. This is actually one of the things that Postgres, again, going back to Postgres being extensible, as I said, Stonebraker was the guy that sort of built Postgres, but he built the first system, Ingress, and when they went to go sell Ingress to the banks, they were like, great, you have date types, we need that to compute interest. But it was all the Gregorian calendar, and the banks are like, where's the Julian calendar? And they're like, we don't have that. So they had to go back and modify the Ingress source code to add support for the Julian calendar as an explicit type. In Postgres, to go back, modify the Ingress source code. In Postgres, they had these user-defined types. So now, if you implement according to their API in C, you can load in your own custom types, and then specify what the operator should be, like plus, minus, and so forth in division, based on that type. Right? And that user-defined types are widely used in systems today. So the Julian calendar is important. It was super important in banks, maybe less so today. Right? So if you go to SQLite, we can take the current timestamp and get again the number of days since Caesar's birthday, and you get back the number you want, and then you just cast it to an integer to make it round. When I asked ChatGPT, it gave me syntax I've never seen before, where I can go say Julian day, but rather than giving a timestamp, I give it the string now, right? And then I can then also convert a date from now based on the start of the year to get the beginning, right? And it computes the same result. Again, I don't want to harp on this too much, but this is a pretty basic thing, but everyone's wildly different. Okay. All right, so we only have half an hour left. So I'm going to skip output redirection, because you don't need this for the homework. But basically, you don't always have to have the output of a query come back to you, to the client, the thing that invoked the query. Like either through the terminal I'm showing here or your application code. You can actually have the data system write it into another table. Right? So the into clause, you can say, take whatever the output of the select query is and put it into this table here. In MySQL, you can actually create the table and have it be populated with whatever the schema is. So it infers through the select query, since it's declarative, it knows what the types of the data you're accessing. It knows how to populate or set up that table on the other side. Postgres, you can actually create temporary tables like this by adding this into clause right before the from. I'm going to skip all this. There's basically, you can do distincts, order bys, which should be pretty obvious, by column names, multiple ones. And then I can get, you can do limits or get the first number of records you want. And do jumps and offsets. You ever see like pagination in web pages, like search results shows you the first 10, you click next, shows you the next 10. They're doing it through techniques like this. And then you can handle ties and other things. Okay, so let's get now to the good stuff, window functions. So I forget when window functions were added. They're probably in the last 20 years or so. But it's like an aggregation where instead of an aggregation where it collapses all your tuples down to a single scalar value, the idea of a window function is that you can compute an aggregation in a rolling manner, still retain the output of the tuples that you're scanning or in your query result, but then you can update that aggregate result as you go along, right? So you want to compute like a ranking of records, or a moving average, or a running total, even a row number. You could use a window function. So the way to think about it is like the function name for the window function will be like an aggregation, or a special one like rank or row number that's specific to window functions. And then you can specify how you want to slice up the data or group it or even sort it to produce the result. Right? You can think of the over clause as like a group by. And this is super common when you're doing time series analysis, when you want to like compute a moving average of a stock price or something like that. So you can do all the aggregation functions that we talked about before, min, max, average, and some account. But then the special ones are going to be row number and rank. Now row number is a weird one because, as I said, SQL is based on bags. There isn't an order. But obviously sometimes you want an order. Or you want to know the position of a record or of a tuple in your output, and row number will give you that. Rank is similar, but it's like the ordering, it's the position within the sort order. So in this case here, I can do a select star from the roll table, where I'm going to get all the values of all the attributes for each record, but then I'm going to have this window function that says, what's the row number? Like, where does it appear? Right? And you would get output like this, where they have this column at the end that gives you the row number. Just 1, 2, 3, 4, 5. So this over clause is going to specify how we want to group these tuples together. And instead of calling it group by, they call it partition by. But the idea is basically the same. So now here I can say, give me all the records in the roll table, and I want the course ID and the student ID, but I want to partition them by the course ID, and I want their row number. So the idea is like, what position are you in each course, right? And you would get a result like this. And now you can see the row number will basically resets every time it switches into a new partition or new bucket. You can put order by clauses in the over output, right? And this is basically it's a way to sort the results, then compute the window function you want over the sorted data. So an example like this, we want to find the student with the second highest grade for each course. You couldn't do this without a window function because you don't know what it means. There's no notion of like what my position is in the course and how to get the second one, because there is no there's no concept of a row number within an output. I'll get the output, if I just do an order by clause, I can get back to my client, to my terminal, things in an order. But within the SQL itself, I have no way to say I'm the second one, the third one, the fourth one, unless you do a window function. So this in the over clause here, we're going to group by the course ID, then we're going to sort by grade, and then now we're going to have our rank position. It's going to be again where does a record exist in that within that partition or group. And then now, since ranking is going to give us our position, now we can reference it in the where clause of the outer query. These are nested queries. I'll see that in a few more slides. But in this outer query here, I can reference the rank that I computed to give me the second entry. Right? The offset of the rank is going to start at 1. Yes.
Sorry, but the keyword ascending, does that sort as from low to high?
This question is the keyword ascending here. Is that low to high? Yes.
Then ranking number 2 is the second lowest, right?
So you're going by, it should be descending, yes. Yes, it should be descending grade. I forget whether it's A or B. The grades might be A, B, C here. Oh. Yeah, so that might be why that's the case. But yes, ascending or descending would change the order of that. Let's check. I'm pretty sure it was A, B, C. So we'll do this in Postgres to start with. Again, because it's always the right way to, it's always the best thing to start with. So let's see the grades enrolled. Right, they're letter grades. All right, so I put my my query in here, and again, so I'm going to get in the inner query here, I'm going to get the select star, get all the records, and then compute the rank of them within the course order. So if I do this, I'll remove the outer query. So I won't sort by, I won't filter by the ranking, and I'll just run the query. So here's the yep, like that. So here, this is the raw output without that filtering. So I'm grouping by the course ID and the partition by, and then they're sorted by their grades, and the rank is going to be their position in the grade. And you see in this case here, 2 people got A's in 721, so they both had the rank of 1, and then the next record starts at 3 instead of 2. Right, there is no 2 in this case here. So let's try that in all our different database systems, see what happens. This is so in the early days of this course, when I give this demo, a lot of these didn't support it. So this doesn't have it. Yep, MySQL doesn't like it. SQLite should do it. Yep, SQLite can do it. DuckDB should do it. Yep. Oracle, probably not. Nope. Oh, because of the as. Another as. Yep, yep. Still doesn't like it. All right, SQL Server should do it. Yep, and then ClickHouse should do it. Yep, ClickHouse can do it. Good. So all of them but MySQL can do this, and Oracle. All right. So this example here was of a nested query. So you have this inner query here and the outer query. So nested queries are another super important aspect in SQL, and it's going to allow us to do really complicated things. And so a nested query can basically appear anywhere inside of a select statement, right? So you can put it in the from clause. So we refer to as the calling query, the outermost query is considered the outer query, and then whatever's inside of that would be called the inner query. But again, an inner query can have its own inner queries. So you can nest these things arbitrarily deep. But you can put it in the select output. You can put it in the from clause, almost as if it's like a temp table you're referencing. You can even do weird stuff like put it in the order by clause, right? This is meaningless, right? This is like getting the max student ID as a number, and then you're sorting things by that number, right? You can do sort by 1 plus 1. It doesn't mean anything because they all going to have the same value, right? But again, you can put it anywhere. And we'll see later on when we talk about query optimization that this is nested queries, especially correlated nested queries, are going to be the thing that chokes most database systems. Because the dumbest way to execute these queries is just for every single tuple in the outer query, rerun the inner query, right? And what you really want to do is rewrite it to be a join. If I look at what I'm doing here, like I say this one here, so I'm doing for every single student in the roll table, I'm doing another query to go get their name. Well, I could just rewrite that to be a join on the roll table and the student table, and then I can do joins efficiently, and that'll run fast. The dumbest thing to do would be for every single tuple in the enroll table, rerun this thing one by one. MySQL used to do that. And there's some cases where the different database systems will end up doing that too, because they can't reason about what the query actually wants to do with nested queries, and ends up falling back to the slowest thing. Yes?
From a query optimization standpoint, is this faster than doing like a temp table with the keyword with than selecting from that temp table?
Her question is doing a nested query being as fast as using a temp table with, being a CTE, we'll get to that in a few more slides, is this going to be faster than a CTE? I don't know, right? Because it depends on what the query plan is, right? At this point here, we're just trying to define the SQL to produce the answer that we want. How good the query plan is going to be left up to the optimizer in the database system. So what I was saying is like for any arbitrary subquery or nested query, most database systems cannot handle them correctly. There's only two systems can. Umbra, which is now commercialized as CedarDB from the Germans, and then DuckDB. But the DuckDB copied what the Germans did, right? I don't mean that disparagingly, like it's all in the papers, they did it, right? And actually DuckDB couldn't do everything, and then our students send them patches to handle lateral joins correctly with nested queries. So DuckDB is probably the best open source one that can handle this now. And it's always going to try to rewrite it as a CTE, or sorry, as a join. With CTEs, you're also going to try to rewrite them as joins as well. But for today, we don't care. We don't know. All right, so let's try to get the names of the students in 15445. Again, this is going to be stupid because like you just rewrite this as a join without the nested query. Yara, yes? This one.
Yeah, that one. Were you putting into the different, I'm sorry, I don't know what the word, start with P?
Partition? Or what?
No, like the thing that you put the function into, the query. Like the MySQL.
Oh, the terminal.
Yeah, the terminals.
Yes.
Different terminals. It looked like it was giving different answers for the ones that it ran for.
Why? All right, so the statement is when we ran this one query, we were getting different answers. So let's double check that. So this.
Like that one has like 6 lines and it has like a 3 in it, and then I think another one had like 5 and it only had 1s and 2s.
Yeah. Let's make sure we have all the right data. So select star from. So what's that? 1, 2, 3, 4, 5. Oh, yeah, I may have an extra tuple from an earlier demo.
Oh, okay.
Like Taylor Swift might have taken a class. Yeah, I have an extra tuple. Yeah. I can show a demo next time. with nested queries, you can get weird evaluation orders of things. Like if you have a nested query that references like an aggregation, when does it compute the aggregation before the tuples get processed or not? Like I'll show a demo next time. Like you can get wrong different answers. Let me come back to that. I think of one where we show. There's definitely rounding issues as well. We can see those. Yeah, so let me come back to that, and I'll show other examples. Okay. Okay, sorry. Okay. So, right, we covered this, nested queries. So again, this example is kind of stupid. Like we're trying to get the name of students that are taking 1545. We could rewrite this as a join, but say for simplicity, we're going to write this as a nested query, and then we could use this in clause to basically say this in operator says, give me and match any tuple from the outer query from the student table if it exists in the enroll table for the for 15445. And so what's happening here is that now the scope of the student ID, the SID field or attribute, is going to depend on where we are in the nesting of the query. So in this inner query here, the student ID is going to be from the enroll table, and then in the outer query, the student ID is obviously from the outer table. Yes.
So speaking of efficiency, is that same as join?
His question is it the same as join? Let's find out. So in SQL, you can actually ask the database server to give you the query plan. So let's see, what query was this? It was the in clause, right? So here's Postgres, right? I can do equals any, or that's equivalent basically to in. So let's do in, right? And produce some input. So if I put the keyword explain in front of a SQL query in Postgres, you'll get back the query plan, right? So these are basically almost like the relational operators we talked about before. This is how the data system is going to execute this query. So it tells you, sort of visualize this as a tree. It's going to do a sequential scan on the student table, a sequential scan on the enroll table, and here's the filter looking for 15445, and then it's going to do a nested loop join to compute the result. Think of that as like two for loops. So for every tuple on the student table, check to see whether there's a match in the enroll table. So we can see what other database systems do for this as well. So go to MySQL, right, and you get something like this. That's not really useful, right? And it has a warning. So let's see what that warning is. Complains about something. It looks like it told me that it rewrote it as a join. So to get the full plan, you got to do explain format equals tree. Yep, there we go. So in this here, it tells it it's doing a nested for loop just as before, but actually now it's going to do a index lookup on the primary key on student ID. So for every single tuple in the enroll table, it's then going to probe the student table on its index to get a result. So it's a nested index nested loop join. So let's go to SQLite. Let's do the same thing. All right, let's first make SQLite can actually run this query. Sorry. These different terminals, like sometimes like you can move faster with the control keys, sometimes you can't. So SQLite will execute it. I can't put explain. I get this. What's this? Right? So the way SQLite is actually implemented is they convert the query plan into their own opcodes. So if you know like the JVM, right? And they have basically a virtual machine inside of the database system that then interprets their own programs, right? It's genius, right? Now he didn't invent this idea, right? Actually, IBM. We'll say this through the entire semester. A lot of things that seem new, IBM did in system art in the 1970s. IBM used to take your query plan and convert it into assembly, and then they would run, instead of like interpreting the tree and walking the tree, they would just run that assembly code. So think of it almost like it would generate a code that would be hard-coded for your query, and it would run that super efficiently. So SQLite is basically doing the same thing, and this allows him, when I say him, Richard, this allows the SQLite guy to ensure that like no matter what weird hardware SQLite is running on, because it runs on almost everything, right? It runs on all the airplanes, it runs on satellites in space, right? It's on everyone's phone. That like all he needs to do is change make sure that the VM works, and that no matter what query program he gets, it can run anywhere. So if you need to get the full plan, I think we got to go explain query plan. Yep, and then we get the tree, right? I don't know how to do this in Oracle. We could ask ChatGPT, but in InductDB, I call explain, and it'll actually give me a nice. Every year, you guys go, oh, amazing, right? It's just Unicode, right? It's not anything that it's not mind blowing. Oracle, I don't think you can do this. Yeah, we have to ask ChatGPT. And then this is ClickHouse, right? The merge tree, like this is again a good example of the data independence. Trees can be organized in different data structures. So this is telling me I'm reading from the merge tree data structure for my table representation. But no matter what the SQL is, I don't have to rewrite the SQL if I change the syntax. And then for SQL Server, I don't think it's going to work either. Yeah. So here, let's go ask ChatGPT. I mean, this is the way of the world, right? Why wouldn't you do this? How do I run? Wait, what's up? All right. Wait, what? Oh, because my search? All right, look. All right, explain plan. Oh, I hate this. Yeah, I remember this. Yeah, so if I call explain plan, it's going to, this is super annoying. So in all the other servers, I call explain plan, and it would give me the output. Was it 4? Right? Explained. So then, yep. So then I got to go back and I go select star from plan table. Yeah, so it's in there, trust me, right? All right, I forget what was the point. What was the question? Oh,
Same as join?
yeah, it's going to get rewritten as a join. Yes, yes, if they do it correctly, not always. All right, so again, these are different ways to access tuples in nested queries. So you can say match all, where I don't care, all the tuples have to satisfy my subquery. Any means at least one. In is equivalent to equals any. Like I can do like equals this, less than that, any. And exist is just saying, give me back any tuple, I don't care what it actually is. So if now we get the names of the students in 1545, I could do in, I could do equals any, right? And it's all equivalent. So let's now do something more complicated. Let's try to say, find the student record with the highest ID that has enrolled in at least one course. Again, you wouldn't be able to do this easily in just regular SQL without nested queries, because you need to know that something at least exists in another set of tuples, right? So this query won't work in SQL 92 with strict mode, because I can't reference, I can't have this aggregate here and reference name without doing a group by. If I do a group by on name, that would be sort of meaningless. It doesn't give me what I want, right? So the way to sort of write these nested queries is you sort of least conceptually how I do it is you start with sort of the outer thing of what I want. Like I want the student ID and the name for the student table. And then I have some where clause that says, I'm just writing in English what I actually want the answer to be. So I want to know that the student is enrolled and has the highest student ID. And then now I could write what that inner query is going to be. And then now I just need to figure out how do I match the record from the outer table from what the inner table is going to compute for me, right? So in this case here, oops, sorry. It's missing the equals any here. But again, it's just a way to take tuples from the output for the outer table, for the outer query, and match it to things on the inner query. In the sake of time, let's skip this. But this is basically like, doing further examples of this. I want to get to lateral joins because you need that for the, you need to know this for the homework. So when you have nested queries, the inner query can reference the outer query tuples, but the outer query can't reference the inner query tuples, right? Because it's running on the inside until it's materialized to the outside. You can't do anything with it. And if I have now multiple nested queries, I can't have them sort of look into each other to figure out what they actually have, right? I just have to have this sort of strict tree nesting. So where lateral joins come in is allow me to have one query reference data or tuples or attributes from the previous nested queries that appear before it in my query plan. So let's say I have a really simple example here. So I just want to have I have a nested query, select 1 as x. So it's a single tuple with one attribute with the value 1 and some temp table t1. And then now I want to just add 1 to it in a next nested query. So if I add this lateral keyword, now in my inner query here, I can reference things that were computed from the queries that appeared before it. And this seems kind of bizarre in the case of SQL, as we talked about, because they're not really supposed to have this ordering of how things should be executed. But lateral is imposing upon that, allows us to say this thing has to be computed for this other thing can be computed. And whether or not the data set decides to run actually these in parallel, if you write them or executes them in serial order, it doesn't matter. It's just from the computation of the answer that we want, we know it has to be done in that order. So we open up, let's open up Postgres again and see what it looks like. So right, so what am I doing here? So I have select 1 as x. Again, this is going to make a synthetic table, a virtual table that has one tuple with one attribute x. And then now I want to add 1 to it as part of my next output. So if I had this lateral keyword here, right, after the comma I say lateral, and then I then specify what computation I want. But now I can reference t1, which is computed over here, within this nested query, and get the answer that I want. If I remove that lateral keyword, right, it's going to complain because I'm trying to reference t1 in this other query here, and it's not there. And it nicely tells me I should be using lateral. So I think I can do this in most of these systems. MySQL can do it. SQLite can't do it. DuckDB should be able to do it. Yep. Oracle, nope. Oh, the as's. Well, we'll skip that. In SQL Server, they don't like it because they don't have the lateral keyword. They have cross-apply, which is basically the same thing. And then I get the answer that I want. But also, what's sort of confusing is I say as t1, then cross-apply, and then with my nested query, but I don't have a comma. When I defined the lateral join in Postgres, there was a comma. And I think the SQL standard says there is a comma. So for whatever reason, SQL Server does it differently. I think SQL Server came out with this first, and then the SQL standard deviated from them, but I might be wrong. And then ClickHouse can't do it. OK, so let's see a more complicated example. So say now I want to compute the number of students enrolled in each course and the average GPA for them. And then I want to sort them by the enrollment count in ascending order. So I want to get all the students in each course get their average GPA, and then rank that listing by the by the number of students that are enrolled in that class, right? To know like if the class has a lot of people, that I'm ranked first or not. So there's basically two subqueries we want. Then for each course, we want to compute the number of enrolled students, and then also for each course, we want to compute the average GPA of the enrolled students from above. So you could write this as two laterals here. In this first part, right, where we can reference, we're producing the output that we can then, we're referencing up here in the CID. So the inner query here is referencing what's coming out of the outer queries from the slum calls here. And then the bottom query down here, it's now going to reference the same thing, but it also can reference anything that was computed in the one before it. Right? And then we get our answer like this. It's a way to think of it, a way to have like for loops within SQL that are executed in order. Yes.
Why do we need the second lateral?
You don't need it. You're just showing how to do it. Yeah. All right. So the last thing is common table expressions with the thing that she brought up, sometimes called CTEs. And think of this as like a way to specify a temp table within your query whose scope is only within that query that's invoking it, that allow you to then reference it in other parts of the query. So a really stupid example would be I can define a CTE where all it does is call select one, produces a single tuple with no name, with no column names, or just with the value of 1. And then now down below it in this select clause here, I can reference my CTE as if it was a table, and then get any result I want out of it. Yes?
So for lateral join, is it kind of like I create a table from the subquery and join them together?
This question is, for lateral joins, is it like creating the table?
Yeah, like we lateral join like two subqueries. Can I say it's kind of like I create a temporary table from the subquery and then join these two temporary tables?
So it's crazy. The statement is, should I think of lateral joins as like creating a temp table, and then I can then reference it and do joins in other parts of the query with lateral joins? At a high level, conceptually, yes.
Okay.
But the lateral join is specifying that the first, this first part here has to get executed before this one does, at least conceptually to produce my result.
Okay.
But it could, then again, the data system could just rewrite it to be joins.
Okay.
But you don't know, you don't care.
They're doing the same thing.
When you say do, like
same.
it depends on again, like, I don't want to get too much in the weeds of like how these systems are implemented this. That comes later. But like, does it produce the answer you want is what you really care about right now. How it's actually going to be implemented underneath the covers, we'll cover later. Because like I said, it's going to try to rewrite it as joins, but not always. It can't always do that. And if you're curious to know what it is actually doing, you just call explain and see what it actually wants to do. Yes?
It seems that temp tables are doing things that are really similar to nested queries.
Its statement is, are temp tables doing the same things that are very similar to nested tables? Yes, but a temp table will persist for the session. So if I open up the terminal and I call create temp table, I can put stuff in it, and then I can run multiple queries and still reference it. And then when I close the session, it gets blown away. But like a CTE or a nested query, its lifetime is only for that query.
It seems that temp tables make code also cleaner, so why would we not just use temp tables?
His statement is, it seems like temp tables make code actually cleaner. Why not always use them? Why do you think it's cleaner?
Because it's not nested, it's like outside, kind of.
His statement is because it's I think you're saying like you define the query or the temp table outside of the thing you're trying to invoke on it.
Like a helper function, basically.
It's like a helper function. It depends on what you want to do, right? In some cases, in some cases, it may be better to define that temp table you're right, and then have multiple queries invoke against it because you're not materializing over and over again. In other cases, it may be just more efficient to put everything, tell the system all at once what you want to do, and you can try to figure out the best plan for it. It depends. All right, quickly, CTEs, which is a gnarly concept, but we'll get through it quickly. But it's not that difficult. Think it's like a temp table again that you can reference within the query. So you can bind an alias of things. So I can say the name of my CTE is CTE name, and then I can say the output of whatever's in my inner queries here is going to be column 1, column 2, and I can reference that down below. In Postgres, I think you can actually give them the exact same name, and it'll still work. MySQL doesn't let you do this, but Postgres, when I tried before, lets you do this. Don't do it. right? That's a Postgres-only thing. So if you go back to say find the student with the highest ID that's enrolled in at least one course, right? I could say for in my CTE, get the max student ID from the enrolled table and join against that. And then it's going to get rewritten as a join, but conceptually I can think of like, it's like the nested query. Think about instead of starting from the outer query and say this is the answer that I want, then figure out how to do the inner query. You're starting with the inner query first. I want the max student ID from the enroll table, and then I write the outer portion of it. It's just a different way of thinking about how to solve the problem. Okay, so let me finish up. If you talk about a lot of these different differences, there is, again, the SQL standard. You can go buy it. It's a lot of money. If you're working at a company that's building a database, they will buy it for you. But we'll take it offline. There's ways to get it for free. All right, so SQL is so important. SQL is the most important programming language, I think, right now. And again, it's going to be here. It was here before you're born. It's going to be here after you die. This is from a survey from 2023 from IEEE, basically saying what do people, they ask programmers, what is the most important programming language they need to know? SQL is always at the top. They always have that SES Jeopardy, or I think when they have like the talent day, and they poll the students, what's the most important programming language? And every year I say SQL, and every year it doesn't rank. Trust me, SQL is way more important than standard ML or OCaml. Okay, so yeah, I said that. And then sort of what we saw today is a bunch of different tricks to try to do as much of the computation within a single SQL query, rather than having to go back and forth between the application code, or the terminal, and the data server. Homework 1 is coming out today. You're going to have to implement I think 5 SQL queries in both SQLite and DuckDB. Right, the syntax will be mostly the same. And what'll happen is you'll run the SQLite, you run in the DuckDB. One of them's going to be faster. Let me take a guess which one's going to be faster. DuckDB, why? Let me take a guess. Nobody knows. Great. This is what this class will be about. So we'll come back starting on what's today's Wednesday. On Wednesday next week, we'll start talking about what the internals of a data system looks like, and we'll understand why DuckDB is going to be so much faster than SQLite for those queries. Yes.
So are we allowed to have only one version for 2 of those DB, or can we write different versions for?
His question is for SQLite and DuckDB, do you have to write?
The exact same.
No, it does not have the exact same, because the syntax, like we saw, syntax is not going to be the same. But what I'm saying is that the variation to go from SQLite to DuckDB, like whether or not you start from DuckDB to go to SQLite or SQLite to DuckDB, I recommend starting with DuckDB. But like it doesn't, they're not going to be the same. Okay? Any questions? All right. So next class, again, we start with the internals of the data system, and we're not going to talk about SQL ever again. See ya.
I need something refreshing when I get finished manifesting. Too cold, a whole bowl like Smith & Wesson. One chord and my thoughts hip-hop related. Write a rhyme and my pen's intoxicated. Lyrics are quicker with a sip of more liquor. Since I'm a city slicker, brain waves are quicker. Rhymes I create, rotate at a rate too quick to duplicate. Feel a breeze at escape. Mics at Fahrenheit when I hold it real tight. Then I'm in flight, then we ignite. Blood starts to boil. I heat up the party for you. Let my girl rub me and my mic down with oil. Record still turns with 3rd-degree burn for one man. I heat up your brain, give it a suntan. So just cool, let the temperature rise. To cool it off with St. Ides.